Hello, so my name is Kamya Yasani, and we have Caroline Rang and Yukon Jin here, and we're going to talk about hierarchical clustering today. So hierarchical clustering in class, we learned about k-means clustering and spectral clustering. Hierarchical clustering is another approach that groups objects and clusters based on a similarity, and we produce a situation where we relate clusters together, and that's something that k-means really lacks, as we do not understand the connection between different clusters. In hierarchical clustering, we have two main approaches: agglomerative and divisive approach. In agglomerative approach, we have a bottom-up situation where we consider all data points as basically singletons, as single units, and we start merging them together to achieve our final clustering. In our divisive hierarchical clustering, we have a situation where we start with the whole data set and we recursively go through and split the data points, so we end up with single points at the end. Today, we're going to talk about the most common type of hierarchical clustering, which is called agglomerative clustering.
All right, so as we mentioned earlier, that the dendrogram is a very useful tool to visualize the clustering result, and it is a tree-like diagram that records a sequence of merges or splits. And here is, as you can see, is a cluster result, and it's not very easy to see which two cluster together, but with a dendrogram, as on the left, you can see that 0.1, 3 are clustered first, and then 2 and 5, and then they are merged, and then 2, 5, the cluster of 2 and 5 merged with 4, and then they all merged together with 6. And so here's an problem. So as you can see, there is a dendrogram. So which set of points yield the first clusters? And that's right, it's A and B. And then if we have 3 clusters, what are the corresponding points for each clusters? And that's right, it's A and B and C and D, F. And the common way that I find useful is to, if you want to have 3 clusters, is to cut a line horizontally and count the number of lines on that cut. And next, before we dive into the algorithm, there's another important notion that I want to mention about. It's the proximity matrix. So it's kind of like what we've learned in the in before. So given n data points, and this is an n by n matrix where each entry encodes the similarity between data points, or we learned before as a distance. And the often used metric is L2 and L1 norm, and also cosine similarities. And in the later examples, you will see that we will calculate the Euclidean distance between points. And why the proximity matrix is important, because it decides how to merge clusters.
So next up is the algorithm. The basic algorithm for the agglomerative approach is very straightforward. So first, we start from the bottom up, where each data point is a cluster by itself, and then we compute the proximity matrix of it. So here is kind of how it works. So as you can see, each point is a separate cluster. We call it P1, point 1, point 2, point 3, etc. And we'll calculate the distances between each point. Then the next step is repeated over and over again, but you merge the two closest clusters and you update the proximity matrix until only a single cluster remains. So what this looks like is, as you can see here, we have 5 separate clusters, and just by eye, you can see that cluster 2 and cluster 5 are the closest together. And then once we find that out, we merge the 2 closest clusters, which is in the second picture, cluster 2 and 5, and we create a merged cluster, and we eliminate the 2 separate rows and count that as one single row. So now there are only 4 clusters left. And we do this step over and over again until only 1 cluster remains. So this brings up the question, how do we update our proximity matrix? How do we define the distance between 2 sets of points? And in the next few slides, we'll see how different measures will yield different clustering results.
All right, so the here comes the major problem about how we update the proximity matrix. So it turns out that linkage is really important in the agglomerative clustering. So we'll talk about 3 commonly used linkage, which is a single link, complete link, and a group average. And the linkage calculate the similarities between 2 clusters, which is important for us to merge or divide the clusters. So I'll go ahead and talk about the single link. So the definition of single link is that the distance between cluster X and Y is the minimum distance between any object X in cluster X and any object Y in cluster Y. So as you can see from the diagram here, the cluster between the distance between these 2 clusters are actually the distance between B and C, because they are the smallest distance. And we'll show the single link by an example. So this is a data set that we came up with, and on the right, you can see the proximity matrix. So one thing you might notice about this proximity matrix is that we set the similarity between the point and itself to be infinity. And the reason we do this is due to practical considerations, because in implementation, if we set the similarity or distance between the point itself to be 0, which is true, then it will always try to cluster itself. So that's why we set the similarity between the point itself to be infinity and only look at the distance between the point and other points. As the initial step, we calculate the distance between each data point, and we found that D and D and E has a smallest Euclidean distance, which is 0.71. So we go ahead and cluster them together. So that gives us another cluster which consists point D and E. And the way we update the proximity matrix is that notice in the previous slide that the distance between D and A is 1.58, and the distance between E and A is 1.41. So we update the distance between A to cluster D union E to be 1.41, because that's the smallest distance between this cluster to point A. And repeating this step, we found that the smallest distance between this cluster to the rest of points is 1.21, which is the distance, which is a point C. So then we class C with this cluster, and then repeating the steps we talked about earlier. We just keep continuing update the proximity matrix using single link, and then find the shortest distance, and then here's the final result. And then here's some pros and cons for single link. First of all, it can handle non-elliptical shape. As you can see from the right top, it clusters this kind of data sets pretty well, and it's efficient to implement because all you need to do is find the distance between 2 clusters, the smallest distance between 2 clusters. But it's really sensitive to noise and outliers. As you can see from the bottom, the cluster doesn't give a really good result because of the huge amount of noises.
So the next linkage example that we have is the complete link. And the complete link distance is defined as the maximum distance between any object X in cluster X and any object Y in cluster Y. So from the little diagram here, you can see that between 2 clusters, it would be the distance of the farthest points from each other, which in this case is A and D. So using the same data set that we did before with single link, we're going to go through the calculations and see how complete link would work. So because we also start with individual points as clusters, the closest Euclidean distance is once again between D and E. So we clustered that together, and we merged the two points into a single cluster that we now color red. And then the next the next closest distance that we have, it's between A and C, which is 1.50. So the way that we calculate this is now between the merged set, we calculate the maximum distance. So we take the distance between the red point on the right side as opposed to the middle red point because from C, because that is the furthest one. And as we go down, we see that C and A are the closest together, Euclidean distance. So we merge those two together into our next cluster. And then we find that the closest distance is between the merged cluster of D and E and F, and we merge that together. And we also find that A and C, the two merged clusters are closer to each other than the outlier, which is in yellow. So we merge that into one big cluster. And finally, we merge that cluster with the yellow point to create a single cluster. So pros and cons of this linkage is that the pros are that it creates more balanced clusters with equal diameter, and these clusters are less susceptible to noise and outliers. So in the top picture, you can see with a lot of noise and outliers, it still successfully manages to cluster them into two groups. And the cons are that it tends to break larger clusters because it creates balanced clusters with equal diameter, and all clusters tend to have the same diameter. So to our point in the bottom picture, you can see that with a small cluster and a huge cluster, it'll kind of split it up so that both clusters are of equal diameter, and that's not how we would expect to cluster these two clusters. The next linkage example, common linkage example we have is group average. So the group average distance is the average distance between any object X in cluster X and any object Y in cluster Y. So from the diagram, you'll see we'll take the distance between B and C and B and D and A and D and A and C, and we'll average these distances out to create the numbers for our proximity matrix. So here is the same data set that we've been using as our example, and in the first step, once again, D and E are the closest in terms of Euclidean distance, and so we cluster them together and we create this cluster. And then next up we have the closest distances between the cluster D and E and C. So we merge those two together to create one large cluster. And then the merged cluster is closest to point A. So we merge that together to create a large cluster. And then the closest point to it in terms of proximity matrix is point F, and so we would merge that. And finally, the only distance left is between the large merged cluster and point B, which is the outlier. So and we create a single cluster again. So this example was very similar to the single link example in terms of which points were added to the cluster in which order, just because that's how our data set worked out. But from the proximity matrix, we can see that the distances calculated were less extreme. They were all closer to each other, which is what averaging the distance tends to do. So, yeah.
Yeah, so I thought it would be better if we go through some examples of our three linkage methods on some data sets and see how they perform. So as we mentioned, single linkage considers basically it only requires that a single pair of objects be close for two groups to be considered close together. So that means only a single pair can decide how close two clusters are. And this basically, with this type of single linkage clustering, you can basically get away with, you can basically violate the compactness property, which means you really don't have to have really compact clusters, and you can really increase the diameter of your clusters. And as you can see in these examples, all the single linkage examples, you really have like clusters that are kind of prolonged, they're kind of stretched, and you have the freedom to increase the diameter. The other extreme is complete linkage, where you kind of take the extreme compactness, you want to take compactness to extremity and really minimize the diameter of your clusters. As you can see in complete linkage, all the data points that are in clusters are kind of like globs, similar to k-means. They're very close together. For example, in the first picture of the complete linkage, you can see that the linkage algorithm doesn't really allow for the ring to go all the way through and kind of cover the whole diameter. And that's why kind of average linkage comes in to be the middle ground between these two extremities, to make sure the diameter is either not too small or not too big, kind of somewhere in the middle. And that's kind of the most common linkage method used. So on the next slide, I just wanted to compare our hierarchical clustering, especially single linkage with k-means. Single linkage performs exceptionally well, especially if you have basically long clusters, and that's where k-means kind of fails because k-means that's kind of blobs of data, whereas single linkage considers the pairwise distances. So as you can see in this situation, single linkage is performing extremely well. As we mentioned earlier, also single linkage is very susceptible to noise, and we just kind of want to see the reasoning behind that. As you can see in the single linkage situation here, comparing to k-means, in single linkage here, we have some outliers shown in black, and the closeness of the outliers really kind of tricks the algorithm to consider the outliers as its own kind of partition, as its own cluster. And that's why single linkage is very susceptible to noise. If you have some data points that are very close together, kind of separate from the overlapping main data points, it kind of considers those data points as their own separate cluster. That's kind of the error we run into in single linkage. So looking at the implementation, more practical approach towards hierarchical clustering, we have to consider its computational complexity. Hierarchical clustering is slightly impractical on really large data sets because it needs the complexity of the algorithm is O of n cubed, which if you have millions of data points, it's very impractical. And the reason for the n cubed is that in each situation you're comparing each two data points. These are which already gives you n cubed, and you're doing that in n steps. So you're getting n cubed with some sort of smart data structure algorithms. If you use priority queues, you can get away with n squared log n, but that's sort of the best you can do. And it requires a lot of space of n squared for that proximity matrix to work. So this sort of clustering is really applied to small data sets. And it kind of shows its best, especially applying to biological phylogenies. So overall, hierarchical clustering is very easy to implement. Unlike k-means, it does not have an objective function, and we have sort of separate linkage algorithms to use, and they all yield different results, as we saw. As a lot of statistical applications, especially in biology, as we compare gene expression and genomes of different organisms, we need to find a way to cluster these genes. And in the next slide, I have an example of the yeast genome, and you can see the clustering on rows on the left. That's sort of the application of the best application of our algorithm. Thank you so much for listening, and we're ready to take questions.